We go above that. Interesting. Okay, so today we are working on section 3.3. We are going to be working on different measures of variation, The first one is the range, and that's the simplest. The range is simply the difference between the highest and the lowest value. What range is there, okay, in my data? So in other words, if the lowest test grade in here was a 72 and the highest grade was 102, my range would be 102 minus 72, which would simply be 30, okay? Now, keep in mind that that particular measure of variation is very susceptible to any extreme values. So if somebody didn't take the test, the highest score is 102, but the lowest score was a 0 because somebody didn't take the test. See how much that affects my range. So it's very susceptible to extreme values. The round-off rule, very similar to we've seen in other places. We're going to carry it 1 decimal place beyond the original set of data. So if the original set of data is to the ones place, you'll round that to the tenths place as necessary, okay? Okay, standard deviation. Here's the biggie. There's the two formulas. They don't look too great. If it says 3.01, then you would round it to the thousandths. Yes, correct. And be careful when we do these calculations, and we're going to do one by hand, and then I'm going to show you how to quickly put it in the calculator, but that gives you a sense of how standard deviation is found. And we're not going to round anything until the very end. So we're a little more accurate. Okay, so two different formulas you can use for the sample standard deviation. And this is sample standard deviation. So as you know, you don't have to memorize any formulas. I'll give you formula sheets on tests. That's number one, but I'm also going to show you how to do that in your calculator. But it's good to just go through one so you get an idea of what standard deviation means. Because it's an important concept that it measures the variation data is away from the mean. The mean is a measure of center, we learned. And so it's how far away from the center the data is pulled. Okay? So if we took a test, our first test, and I had the mean being 85 and the standard deviation being 5, that would be great. But if I gave the first test and my mean was 85, but my standard deviation was 20, that would mean that my scores are way out there. Okay, a big stream spread or variation in my data. Okay, it is the measure of variation from all the means. Everybody say hi to Hero. Hi. She's my sanity. Seriously. The standard deviation, because it's a measure from spread, that's a distance, so it's always going to be positive. The standard deviation will always be positive. As we saw with the range, one piece of data can make that standard deviation measure much different. So again, like on my test, if I had one student who didn't take the test and got a 0, that's going to make my standard deviation much larger because it's pulling it out. Okay? Important thing here. Units, 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 and units. Jemiah knows, right? You took 129. It was her favorite course. Units matter. The first test, I'm not going to mark your whole problem wrong if you forget units, because it's not as critical right now as it is in a dosage calculation course, because in that kind of course you could kill somebody if you have the wrong units. There's a big difference between micrograms and milligrams. Okay, but I'm still going to ding you for a point or two. The units are the same. The units are the same as what your data is. So if you're comparing test scores, the standard deviation of 5 would be 5 points in the test scores. If you're comparing the heights of people in this room, the standard deviation of 2.8, it would be 2.8 inches because we measured it in inches. If we took everybody's height in centimeters, it would be 2.8 centimeters. So those units are what is in the original data. Okay, so now we get to work. This is the one little teeny tiny one we're going to do by hand. With all of 4 pieces of data. The very first thing, if you look at your formula, the simple standard deviation is the square root of the sum of the x value minus the mean, the whole thing squared, divided by n minus 1. So the very first thing I need to find is the mean, or x bar. So x bar will equal 22 plus 22 plus 26 plus 24, all divided by 4. If somebody wants to do that calculation, pardon me? 23.5 is x bar. Okay? So that's the first thing I need to do. Remember, my sample standard deviation is equal to the square root of x minus x bar squared divided by n minus 1. Okay. N is the number of pieces of data. N is the number of pieces of data. This represents, the x represents the piece, that actual piece of data. X bar, of course, is our mean. So the way to do it is we're going to put columns and we're going to do each thing separately. So, if I can get my board to... There's what I need. So I have a little more space. So the first column I'm going to make is x minus x bar. My first data point is 22. I'm going to subtract 23.5. And of course, when I do that, I'm going to end up with negative 1.5. Again, my next data point is exactly the same. 22 minus 23.5 is negative 1.5. My next data point is 26, so I have 26 minus 23.5, and of course I'm going to get a positive 2.5. My last data point up there is 24 minus 23.5, and that's going to be 0.5. So that's my first step. But the formula says, hey, after I do that, I have to take whatever I get and square it. So my next column is going to be this squared. So I've got to take negative 1.5 and square that. And when I square negative, I get a positive. And that's what I have to do. And the reason I have to do that is if I added everything up, I'm going to come to 0. So I have to square that. And if I square that, I believe I get 2.25. And then again, I'm going to get 2.25. And 2.5 times 2.5 is 6.25. And of course, 0.5 squared is, you should know that one, 0.25. Okay. Oh, and I forgot to write sum. That wasn't good. You guys let me do that, and you're looking at the formula, right? Don't I have to sum all those? $11? Yes. So that's the sum. So next I'm going to take the sum and divide by n minus 1. So I'm going to take 11 and divide that by n minus 1. What's n? 4. So 4 minus 1 is, okay, and we get, okay. But lastly, what do I have to do? And when you do that, what do you get? 1.9. And did you round that? Okay. So all that work, and what did we find out? That I believe these were Chips Ahoy cookies, number of chips in the cookies. We found that the mean was 23.5. We found that the standard deviation was 1.9. That's how far they were spread out. And the reason we got 1.9 was because we had one up there at 26. That's what spread it out a little bit more. Okay? Does that make sense? Who'd want to do that with lots of data? Not me either. But we used to in my old age. We did. We did. It was fun. Okay, so I want to go to the e-text here. And let me grab my picture camera tool, which of course my camera tool is not sitting there. Doesn't want to allow me to capture it. Okay, so this is the one that was captured right from the textbook. Years to earn your bachelor's degree. Listed below are lengths of time in years it took for a random sample of college students to earn their bachelor's degree. Based on these results, is it unusual for someone to earn a bachelor's degree in 12 years? So the first thing we want to do is, I'm just going to use this data. We'll come back to the same problem, but I want to use this data just to find your standard deviation, okay? So let's go to your calculator so we can learn how to do that on a calculator. Okay, so just like we did in the past, we're going to put that data in our stats list. Now you have a choice because you see here that there's many that are repeated. You can either enter it that many times or you can count how many 4s there are and that's your frequency. Does that make sense? I'm not getting a lot of confirmation there. Okay, so let's do it. So my data point of 4 are all those 4s, correct? So there's 1, 2, 3, 4, 5, 6 4s. So I could enter 4 in L1, and in my frequency of L2, I can enter 6. Or I would have to enter 4 6 times in L1. Right, who'd want to do that, right? So how about 4.5? There's 1, 2, 3, 4, 5, 6. There's 6 of those. So these are going to be our frequencies. 6s, there are 2. 8s, there's only 1. There are 2 9s, 2 13s, and 1 15. So in our calculator, we're going to go to our stat menu. And remember, to put our data in, we first have to go to edit so we can edit our lists. My first is going to be a data point of 4. So I'll enter that. My next one is going to be 4.5. My next one is 6, then 8, then 9, then 13, then 15. So I'm just going to enter those data values right down L1. Wait for everybody to get those in. Then I'm going to use my cursor key to cursor over to L2. L2 is the frequency. So how many 4s were there? There were 6. 4.5s, there were 6. 6s, there were 2. 8s, there's only 1. 9s are 2. 13s are 2. And 15s are 1. Everybody good? Now, when you ask this to do the calculation, if you ever get an error that says DIM error, and it means dimensional error, it's because L1 and L2 have a different number of data. So in other words, you left a frequency off or you left a data value off. They have to match. They have to have the same number of items in L1 and L2. Okay, so I'm going to go second and quit to get out of my data. I don't want to mess that data up. Now I wanted to do the calculation, so I'm going to hit stat, cursor over to calculation. And again, it's one variable, stats, so we're going to choose that and hit enter. Those of you with an 83 or an 84 with the old operating system, on yours it just says one variable stat and it's just blinking. You're going to type second L1, then you're going to type this comma, then you're going to type second L2, and then you're ready to press enter. Those of you with the operating system that's on my screen, my list is going to remain as L1. I'm going to cursor down to frequency list, and I'm going to say my frequency is in L2 by hitting second number 2, L2. Then I'm going to cursor down to calculate and hit enter. Who do I need to help? Let's see. Okay, so you have the old operating system, and what you did is you forgot to type in L1, L2. So you're going to go to stat, you're going to cursor over to calculate, you're going to hit enter once, and see where it's blinking here? You have to say second L1, comma, second L2, and then hit enter. Haley, how about you? You got it? Is it, I can't see from here, 6.5? You got it. Is everybody good? Okay, if you ever get an error, go back to those lists and make sure you have the same number of items in each of those lists, okay? So here you go. And just so you know, just as a repeat here, this is my sample standard deviation. So I know my standard deviation is 3.5056. Now, I need to round that, correct? And if I look at my data is here to 0.5, which means I'm to my 10th space. So I need to round it to the 100th space. I have to go one beyond. Okay, so when I look at 3.505 and I'm rounding to my hundredths, that 5 has to bump that up to a 1. So my standard deviation is 3.51. That makes sense? Okay, we're going to come back to whether it's unusual or not once we get through more of what we're talking about, okay? So we'll come back to that problem. Just want to make sure it put it in the right spot. So here we are, the range rule of thumb is that when we're looking at population, if my sample is small, it doesn't necessarily happen because as we saw earlier when we rolled the dice, a small sample doesn't give us a nice curve, does it? But when we add more and more and more and more, it does. So when that happens, the majority of all the data lies within 2 standard deviations of the mean. 95% lies within 2 standard deviations of the mean. Okay? 95% within 2 standard deviations of the mean. So here's the formula, which says the minimum value is equal to the mean minus 2 times the standard deviation. The maximum value is the mean plus 2 times the standard deviation. Okay, what are you doing? You're going to the mean, you're subtracting it twice, and you're adding it twice. That's all it means. Okay? That is my definition of usual. That's my definition of usual. Within 2 standard deviations of the mean. So let's go back to that problem we were just working on. We found our standard deviation of 3.51 rounded. And to find out if years is unusual, because that's the question, we have to find out and do the calculation. So we found our mean is 6.5. So I have 6.5 as my mean. I'm going to add 2 times 3.51. In other words, I'm adding the standard deviation twice. Somebody tell me what that is. $13.52. And I'm going to take 6.5 and I'm going to subtract the standard deviation twice. Now we know in reality that would be very unusual, right? Yeah, bachelor's degree in less than half a year. But according to our stats, anything between 0.52 and 13.52 is considered to be usual. Okay? So 0.52 to 13.52 is usual. So is 12 years unusual or usual? Okay. Definition of usual using standard deviation. Okay. So go ahead and I want you guys to work, and then we'll come back together and see what you think of this, just so you can see it from there. 40 chocolate chip counts for the Chip Ahoy's cookies. The mean is 24.0 chips, and the standard deviation is 2.6. Use the range rule of thumb to find the minimum and maximum usual numbers, and then decide if a cookie with 30 chocolate chips would be unusual. Okay, let's see how we did. So to find the minimum and maximum, to find the minimum, I'm going to take the mean, 24.0, and I'm going to subtract 2 times the standard deviation of 2.6, and what do we find? Okay, and to find the maximum, we're going to take the mean, and we're going to add 2 times the standard deviation, 29.2. So my range of usual data is from 18.8 to 29.2. So would a cookie with 30 chips be unusual? Yes. Good. So not bad, right? Just a note about when we're trying to compare different variations from different samples, we only want to use this comparison when they truly have similar means. Like, for example, a test score with a mean of 85 and a mean of 82, and I can compare those. That would be okay. But when they're drastically different, you don't want to compare them. Instead, we're going to use something called the coefficient of variation, which will be at the end of this section. So that was for sample standard deviation. Here's the official formula for a population standard deviation. Again, if you look at your calculator, the one below the sample standard deviation, theta, is the one that is our population standard deviation. Most often, you're going to have sample standard deviations that you're going to be calculating in here. Okay, most often you'll have sample standard deviations that you're calculating in here. Variance. Nothing on my calculator is going to give me variance, but that's okay because the variance is only the standard deviation squared. That's all it is. It's the standard deviation squared. Remember when we did it by hand and we went through that formula and we summed everything, we squared, then we summed everything, then we had to take the square root of it. Before we took the square root is the variance. So on the chocolate chip example, the chocolate chip example had a sample standard deviation of 2.6, correct? So we're going to take that because the variance is equal to the sample standard deviation squared. I'm going to put 2.6. I'm going to square that. Somebody's going to tell me what that is. I always forget to turn that off. 676. That would be my variance. That would be my variance. And we'll use variance more often in the later part of the course. Just so that you know what the notation looks like, that will be the sample variation, and that would be the population variation. The reason we'll be looking at the variance is because it's an unbiased estimator. What that means is that if I have a sample variance, that is a good indicator of what the population variance is. That's why I would want to use variance, because sometimes the standard deviation itself is not. We'll be talking about that again and later. This is just telling you that we use n-1 instead of n because it targets better. We've learned that over the years that targets better. So now let's get to the empirical rule. We already said that usual was within 2 standard deviations of the mean, and we can find the max and the minimum of what we say is usual values. But here we're going to put some percentages on it. 68% of the mean is within 1 standard deviation of the mean. 68% of all the data is within 1 standard deviation of the mean. 95%, that's that usual, is within 2 standard deviations of the mean. When we go all the way out to 3 standard deviations of the mean, 99.7% of all of our data will be there. 99.7% will be within 3 standard deviations of the mean. I think I have a picture. Good. On the next. So if this is my mean, 1 standard deviation positive and 1 standard deviation negative, 68% of my population is there. If I subtract it twice and add it twice, 95% is there. And 3 times 99.7% is there. So with that, I want to talk about IQ scores. What's an IQ? What does IQ mean? What does that stand for? Anybody? You've heard that term somewhere before, right? Intelligence quotient. Yes, intelligence quotient. Is that a measure of how much we know? Not really. It's a measure of our intelligence, of how well we can think and problem solve, all those things, make analogies, etc. Okay? They've actually gotten to the point now, oh, don't ask me how, because I have no idea. They can actually measure an infant's intelligent quotient. And they have also gotten it so well that it doesn't change usually more than 5 points by the time they're an adult. That blows me away, okay? It just totally blows me away. So your intelligence quotient really doesn't change much over the course, so you can learn more and more and more and more and more. It's not a measure of how much you've learned. It's a measure of your intelligence, things that you can process, thought patterns, problem solving, puzzles. They use puzzles to test it. Has anybody ever had their IQ tested? No? You don't want to know, do you? That's pretty cool, actually. An educational psychologist is a person that can test it. So it is really, really pretty cool. It's a long, involved test. My son had it done just because he was being tested for ADD and ADHD back when he was in 1st grade. And literally the test was 3 hours long. Of course, they tested him, for other things as he was going through that, his processing, his being able to pull it forward, what he had learned. It was very, very interesting, and I got like an 11-page typed report, so Very, very interesting. And yes, he was ADHD all the way to the end of the continuum, but I already knew that, right? So, with that, they gave me an approximation of his IQ. So that's the only reason I know. Okay? So, but we have known through years and years and years of testing over and over and over and over and over again that the average IQ, anybody know? Yes, very good. The average IQ is 100. Absolutely. And does anybody know what the standard deviation is? I know that one. And now we're going to use this. We really shouldn't be using X bar. We should really be using mu because this is population. This is population. So we've done hundreds of thousands of samples, and now we've got the sample of the sample and the mean of the samples and the standard deviation of the sample. So we're going to be using sigma here. And the standard deviation is 15. Okay? So adding 15 gives me 115. Subtracting 15 gives me 85. That means 68%, almost 70% of every person there is in the world, population, has an IQ between 85 and 115. Okay? Well, if I go another standard deviation, so now it's going to be 130 because I've added 15 twice. I'm going to subtract 15 twice and get 70. 95% of the population has an IQ between 70 and 130. Yes. We found that over hundreds of thousands and no, it's just something I know because, yeah. Only because it's IQ scores and I know them. Good question now. Good question. So then one more standard deviation from the mean. Obviously this one's going to be 145 and this one's going to be 55. Okay? 99.7% of the population has an IQ between 55 and 145. Guess what? These people are geniuses. Period. I know two people. I'm just happy I know two people who have an IQ like that. One is a self-made millionaire. One is a friend of mine that went to undergrad with me. And he skipped 2 grades. Seriously. Graduated then 2 years early and went on a scholarship to the Air Force Academy, which means he was selected of one of 2 people from the entire state, and it wasn't the state of Delaware. So then he would IM me and say, give me help with calculus. I'm like, really? So very, very intelligent people. On the very sad end, on this sad side here, okay, and very small amount of people. At 55, we're talking about people who are unable to even provide care for themselves. Okay, so that's the range. 99.7% of the population has been between that. Okay, so I always like to know if you know your IQ before I do that. But yep.
It's confusing me. I thought that all of this was part of the equal up to like 100. Because how come 68 and then 95 for the population and 97?
Well, but there's still some people that are way back out here that are past 3. See, I've still got 0.13% on this little teeny tail here, and I've still got 0.13% on this little tail.
I would figure that the 68, 95, and 99.7 obviously is over 100.
Oh, no, 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 no. Okay. Okay, good. Now I understand your question. If I'm talking about just this amount, that's six, I can't touch the board evidently. That's 68%. But if I expand it, that's 95%.
Okay. I see what
Accumulative as we go.
you're
And then 'cause you were trying to take 68 and then add 95. No, it's just this is 68 within one standard deviation. Then I expand that to 2. Then I move to 95%.
So basically, if you want to find the figure between 85 and 115, you would have to just like subtract it or something like that to find that amount. Well, no.
Right, you're going further into z-scores. We'll get there. Jemiah is talking like, well, what if my IQ was 110? Right? And then I'd have to find the area under the curve and all that, and we will get to that. I think that's where you're thinking ahead. Okay? All right. So that's just to reiterate back here. This is the empirical rule, and that's when I know my population is normally distributed. That's when I know my population is normally distributed. We have another theorem called Chebyshev's theorem, and we use this theorem when for any set of data, even if it's not normally distributed. So, what it's saying for K, and you have to realize that K is within K standard deviation, so 1, 2, 3, 4 standard deviations the mean, it always says that at least 1 minus 1 over K squared has that percentage in its standard deviations. So what does that all mean? So if I'm within 2 standard deviations, it doesn't give a calculation here, so I think that's a little confusing. The calculation says 1 minus 1 over K squared. So 1 minus 1/2 squared. What is 1/2 squared? 1/4. I should have put 1 first, sorry. And what do I get when I take 1 minus 1/4? 3/4, right? 3/4, if I change that to a percent, is 75%. So Chebyshev's theorem says at least 75% in any data set. In any data set. Okay? It doesn't have to be normally distributed. Then we know more about it if it is normally distributed. And within 3 standard deviations, 89%. Okay, so they're a little bit lower percent because it may not be normally distributed. Okay? So I think I already blew it for doing that example because I already used IQ scores because it's one I know always off the top of my head. So we could use it to Chebyshev's, but since we know it's normally distributed, we can still use what we already did. Okay? All right. And lastly, the coefficient of variation for a set of non-negative sample or population data, and we want to express it as a percent. It describes how standard deviation is relative to the mean. And remember, we're only going to use this if our means of our data are different, extremely different. If they're pretty close, we can just take a look at it. But we would use the coefficient of variation if those means are drastically different. And we're simply going to take what does this mean? What does this mean? Of the sample divided by mean of the sample times 100 because I want to get it into percent. For the population, of course, what is this thing? Beta divided by mu times 100. Okay? All right. That is all.